In Chapter 12, we're going to review parametric equations, polar coordinates, and conic sections. In this section, 12.1, we'll start off with parametric equations. And a parametric equation is just an equation, and they're usually in the rectangular coordinate system with x and y values, where we have a parameter t. We usually use parametric equations to describe the position of an object as time goes on. So we usually let t stand for time and x and y be the position of the object. Now, with this parameter t, our curve made up of points x and y will be generated in a certain direction, which we call the forward or positive orientation. So again, that's the direction that the curve is generated in as t gets larger and larger, or as t increases. Example 1, we want to graph this parametric equation for t values that are greater than or equal to 0. If you have a graphing utility or a graphing calculator and you have a parametric mode on your calculator or your utility, you can simply plug these values into your calculator. Well, let's assume that we don't have a calculator. What we can do is we can make a table of values. We can look at our t values and see what happens to x and y as t increases from its starting value of 0. And we'll put a few points in. So if t is 0, my x value is 1 and my y value is 0. Oops. So on my graph, I'm going to plot the point x is 1, y is 0. So that would be when t is equal to 0. The coordinate is the x and the y value. So that would be the coordinate 1, 0, because we're still in the x, y plane. Now let's say t is 1. If t is 1, then x is 0 and y is negative 1. So I have t is equal to 1. The point is the point 0, negative 1. What if t is 2? If t is 2, x is negative 1 and y is negative 4. So we have the point negative 1, negative 4. So it looks like, if I were to connect the dots, that this curve is being generated, or its positive orientation is actually downward. Let me do one more value. I'll do 3 for t. So my x is negative 2 and my y value is negative 9. Negative 2, negative 9. I can see that it looks like this curve is being generated downward. So I don't want to keep looking at larger and larger values of t. If I look at my parametric equation, I can see that as t gets larger and larger, my x values are actually getting smaller and smaller, and so are my y values. So I'm thinking that this curve will continue to go downward. So one way I can determine that without using any technology is maybe get rid of the parameter t, and I'll have an equation with just x and y. Perhaps it'll be an equation that I recognize. So let's say I wanted to eliminate the parameter t. Well, when I look at my parametric equation, I can see that it would be really easy for me to get the t by itself in the equation x equal to 1 minus t. If I solve for t, then I get t equal to 1 minus x. And then I can simply substitute that t value into the equation with y to get y equal to negative, in parentheses, 1 minus x squared. I recognize that as being a parabola. You might want to multiply all of this out to get negative x squared plus 2x minus 1, I think. Okay. So since it's a parabola opening downward, I could see that this will continue to go down, and I don't have to plot more points. So it's positive orientation, or I just like to use the word generated. The direction it's generated in is actually downward. So oftentimes in these graphs, we will put direction arrows in to indicate the direction that the curve is generated or its positive orientation. Now I just say the direction it's generated in because when you look at the word forward, we'll go back up to this box. If you look at the word forward orientation, positive orientation, it sort of implies that it's going to be going forward, so maybe to the right, and all positive values, which is why I usually just say generated. Well, now that we've eliminated the parameter t, I can see the shape of this object, which is a parabola. So if I had to describe this, it would be a parabola. But it's just half of the parabola. So maybe half of a parabola. The vertex, that's usually how we describe parabolas, is by its vertex. The vertex is included in this graph because that happens at 1, 0. And the parabola opens down. If I was to talk about the way it's generated or its positive orientation, which is what my lab will use, it's going to be downward. And I can get even more specific. I could say that it's downward and to the left. So here you might want to go ahead and check using a graphing utility. And you can use a graphing utility for all of these problems. So now what we're going to do is we're going to look at some specific types of parametric equations. We're going to look at circles and lines. Let's first start with our circles. So let's assume that our a and b values are not 0. So one way we can describe a circle is with x equal to x sub 0 plus a cosine of bt, y equal to y sub 0 plus a sine of bt. So this is one way, not the only way, one way we can describe a circle where the center is going to be the x sub 0, y sub 0, and the radius will be the absolute value of a. If it turns out that the b value is positive, then this circle is going to be generated in a counterclockwise direction. Now, if I were to eliminate the parameter t, then the equation without t would be x minus x sub 0 squared plus y minus y sub 0 squared equal to a squared. So that's just the general equation of a circle with just x and y in it. I'm going to mix it up a little bit because remember I said this is one way to describe a circle. In example 2, it says eliminate the parameter to describe the circle or arc. It might not be a full circle in terms of x and y. And then we're going to state the center, the radius, and the positive orientation. Well, what you should notice here is my x value is written in terms of sine, not cosine, and my y value is written in terms of cosine, not sine, and it's still a circle. Notice that if you did put this in a graphing utility, you would get part of a circle. And that's because switching the sine and the cosine does not change the shape of the graph. It changes the direction the graph is generated in. So one way I could change this circle from counterclockwise, notice my b value is 1, it's positive, to maybe clockwise is to exchange the sine and cosine. Another way we can change the direction in this general form of a circle is keep the x with cosine, the y with sine, and simply change the argument to negative instead of positive. And there's other ways we can change the direction that the curve is generated in. So again, remember, this is just one way to describe a circle. It's not the only way. So let's say that I did have my x as sine and my y as cosine. Again, this is still going to be a circle. However, my x sub 0, y sub 0 is not going to change. My 2 is still my x sub 0. And notice that the y sub 0, oops, forgot my little sub 0, is 0 in my y equation. My a value is 1, because the coefficient on sine and cosine is 1. And my b value is 1 as well. So this is a circle. I don't know if it's a complete circle, but I do know that the center is going to be 2, 0. I know the radius is 1. Okay, so let's see if I get the whole circle, because I know my t values are only going from 0 to pi. Well, instead of plugging this in a graphing utility, what I'm going to do is go ahead and make just a few values for my t values and see if, or one, verify that this is actually a circle. And it'll also give me the direction that this circle is generated in. I'll start with t is equal to 0. If t is 0, x is 2, and y is 1. So let me just do a quick little sketch. We're at 1, 2, 1. So here, when t is 0. When t is, let me do pi over 2. I could have done pi over 6, pi over 4, pi over 3. But I look at my sine cosine values and I'm not really using a calculator. I'm doing this by hand. So pi over 2 gives me a nice value. It gives me a 3 for x and a 0 for y. So let me go a little bit more. I'll have a 3, 0 here. So it seems like as my t values get larger, it looks like I'm going in a clockwise direction, which is what I knew would happen when I exchanged sine and cosine. Let me go to pi. Now I'm skipping a lot of values in between for my t values. So if I wanted to go back, if this wasn't enough for me to tell how it was generated, if I wanted to go back and maybe check pi over 4, 3 pi over 4, and so on, I could do that. At pi, I get 2 for my x value and negative 1 for my y value. In my graph, that would be a 2, negative 1, and it looks like it stops there at t equal to pi. So I'm seeing it being generated clockwise. So its positive orientation will be clockwise. And I'm not getting the full circle. What I'm getting is a half circle. So this is actually a half a circle. And a half circle is an arc. The center is 2, 0. The radius is 1. Its generated, or its positive orientation, is clockwise. I'm going to do generated because I'm too lazy to write positive orientation. So it's generated clockwise, but that's kind of not enough. Without this picture, where does it start? So I'm going to say that it starts at, and it started at the point 2, 1. That should be enough because I know it's a half circle, so I'm going to go halfway, and I will have to end at 2, negative 1. But to be more specific, I could say starts at 2, 1, ends at 2, negative 1. Oh, but I was also supposed to take away the parameter. Well, it's x minus 2 squared plus y minus 0 squared. So y squared is equal to the r is 1. So a squared is 1. And that's it. Again, you can always check all of these with a graphing utility, and I suggest you do. Example 3, we want to find a parametric equation of a circle centered at 0, 3 with a radius of 4 and generated clockwise. So the center is our x sub 0, y sub 0, always. A radius of 4, remember that's our absolute value of a. So we could make it a minus 4 or a plus 4 in the equation for this circle. And it's going to be generated clockwise. So one way I could change the direction is to change it from a t to a negative t. I can let my x value equal to, I can have my a value be positive. So x sub 0 is 0. So this is going to be 0 plus 4 or 4. I can leave the cosine and change this argument to a negative t. And that would change it from a counterclockwise to a clockwise. And I'm still keeping the x as cosine, the y as sine. Again, I could also just change it to a sine and keep the t positive, but I'll leave it this way. My y value is going to be the y sub 0, which is 3. I'm going to keep my a value as a positive 4 and do a plus 4. And to change it from counterclockwise to clockwise, I'm going to replace the t with a negative t. And then this is a circle. It's a full circle. So my t values are going to go from 0 to 2 pi. So this is just one way I could describe this. Now remember that cosine is an even function and sine is an odd function. So I could also write my x value as 4 cosine of negative t is just cosine of t. I can write the sine of negative t as pull out the negative, so this is just going back to trig, and get 3 minus 4 sine of t. My t values would still be the same from 0 to 2 pi, and you have to put your t values down here if it says that it's just a circle. You have to have your starting and your ending t values. So again, you can double check, plug this in a calculator, see if you still get a circle that's generated clockwise. Okay, let me play around with this some more just for fun. What if I change the argument and replace t with, I don't know, why don't I just change cosine of t to cosine of 2t? And sine of 2t. So why don't I change my b value? Well, what happens when you change that b value, that coefficient on t, is you're changing your t values. So if I'm going to multiply t by 2, then in my inequality, I have to divide t by 2. So if I divide everything by 2. So now my t values are going to go from 0 to pi. Think about that. If you multiply your t value by 2, that means that your circle is completing itself faster. So it's going to complete at pi, not at 2 pi. Now what if I change the argument to 1/2 t? Well, then I'm slowing down my t values. I'm slowing down the way my curve is generated. So instead I would have to multiply by 2, so then it would go from 0 to 4 pi. See, I could do this infinitely and come up with infinitely many representations for this circle. The only criteria I have here is its center, its radius, and that it's generated clockwise. And all of these are okay. All right, let's go ahead and look at another example with circles. Example 4, we have a bicycle. Ooh, that's going to bug me. I don't have my capital A. A bicycle moves with a constant speed in a clockwise direction around a circular track of radius 600 meters. The bicycle completes one lap in 1.4 minutes. Find parametric equations that model the path of the bicycle. Okay, so I know that it's going in a clockwise direction. I know the track is circular. I know the radius is 600 meters. And I know that the bicycle completes one lap in 1.4 minutes. So that means we have a complete circle when t is equal to 1.4. So I get my t values, 0 to 1.4. Now that's not my usual 2 pi, so I'm going to have to make an adjustment there. Since I'm going clockwise, I have a variety of things I could do. I can keep my x as cosine and my y as sine and have a negative in the argument. Or I can change the sine and the cosine, and I think that's what I'm going to do. I'm going to let my x be sine instead of cosine. Now what about my center? Notice that there is no center here. That means I can choose whichever center I want. So why not make it easy on myself and choose a center of 0, 0. So my x sub 0 is 0, my y sub 0 is 0. Remember, this is not unique, which means x is going to be either negative or positive 600. Because remember, my absolute value of a is going to be 600. So I can choose a to be a positive or a negative 600. So I'll just choose the positive and have x equal to 600 sine, because I'm going to go clockwise, of bt. I still have to figure out what that b is. Because remember, my t values are not going from 0 to 2 pi as usual. It's going from 0 to 1.4, which means I'm going to have to adjust that t value. So instead of having b equal to 1, b is going to be equal to something. My y value is going to be 600 cosine of bt. So how do I figure out what this b value is? Well, remember what we did in our last example. Whatever we had on top of our argument, we divided everything. So we know that our t value has to end at 1.4, which means that b of t is going to, if it ends up at 2 pi, and I know that it actually is a 1.4 for my t value, then I would just divide the 2 pi by 1.4 to get my b value. That would be 20 pi over 14. Typically we don't write this as a decimal, we leave the pi in there, or 10 pi over 7. Now that I have my b value, I can write my equation, which would be x equal to 600 sine of 10 pi over 7t, y equal to 600 cosine of 10 pi over 7t, where the t values are going from 0 to 1.4. Again, this is not unique. So again, you can go ahead and check this and see if you get a circle generated clockwise and you just get one lap of that circle. Well, let's move on from circles to parametric lines. Well, when we talk about a parametric line, remember a line needs a point and it needs a slope. So our point is going to be just any point x sub 0, y sub 0. And our slope is going to be written as a fraction b over a. So one way that we can write the parametric equation of a line is the x value equaling to x sub 0 plus at, the y value equaling y sub 0 plus bt. In example 5, we want to find a parametric description, and this is not unique, of the line segment between the given points. In this particular example, we're not given a direction, which means I can choose any of those points to be my x sub 0, y sub 0. Now, if I was given a direction, if it said you're starting at 2, 5 and you're ending at negative 1, 3, then the starting point would be my x sub 0, y sub 0. But again, I'm not given a direction here, so I'm just going to arbitrarily choose the point 2, 5 to be my x sub 0 and my y sub 0. Now, with any line, you need a slope, your b over a. So we usually use m for slope. Now, when you find your slope, it's always your ending point, subtract your starting point. And I used 2, 5 to be my starting. So my slope is going to be 3 minus 5 over negative 1 minus 2. That will give me a negative 2 over negative 3, which would be my b over a. Now I could write this as a positive 2 over positive 3, but I'm going to leave it exactly as it is. Because remember, this is not unique. If I let my b be negative 2 and my a equal negative 3, then my x value is going to be my x sub 0 of 2. It's going to be minus 3t. My y value is going to be 5 minus 2t. Well, what are my t values? Well, notice when t is equal to 0, I'm at the point 2, 5. What t value gives me the point negative 1, 3? If t is equal to 1, then 2 minus 3 is my negative 1. And the y value, 5 minus 2, is positive 3. So that would be one representation. Or what if I wrote this as positive 2 over 3 and changed my b over a? So my x would be 2 plus 3t. My y would be 5 plus 2t, which is perfectly fine. But this is just a line segment. So where does it start? Where does it begin? Well, when t is equal to 0, I am at the point 2, 5. But what t value gets me to the point negative 1, 3? Well, I could simply solve this algebraically. If x is negative 1 and y is positive 3, what t value is that? So when I solve these equations, I better get the same t value. And I get negative 1 for both. Negative 3, yeah. So when t is equal to negative 1, I'm at the point negative 1, 3, which means my t values are going to go from small to large, right? So from negative 1 to 0. So you see, because I got rid of the negative in the top and bottom of my slope, that means that I would have to add the negative into my t values, which is typically why, if you're talking about lines, you want to keep the slope exactly as you see it. You don't want to reduce it or change it in any way, especially if you're specifically told a direction that you need to go to. Did want to caution you that on my lab, if they ended up with a slope like, let's say 2/4, then they would probably reduce it to 1/2. So that would change that t value. Instead of going from 0 to 1, it might go from 0 to something else. Anyway, what if, let's do this again. Remember, this is just a fraction. Let's say I'm at 2/3 and I decided, I'm going to divide the top and bottom by 2, which I can do. And I would get 1/3/2. That would be my b over a. Remember, this is not unique. There's infinitely many ways I can write the equation of this line. So that would mean x is equal to, we still have 2, but now my a value is 3/2. So it's going to be plus 3/2 t. My y value, it's still going to be 5. It's still going to be a positive, but it's going to be a 1 times t, or t. So how did that change my t values? Okay, well, I was at -1 to 0. I divided my slope top and bottom by 2, which amounts to doing the opposite, which would be to multiply my inequality by 2. So my t value should go from -2 to 0. And you could check that. If you put in -2 for t, you're at -1. Yeah. And 3. If you put in 0 for t, you're at 2, 5. So you still have the same line segment between the 2 points. Again, it's just a matter of changing the direction. If you don't see that, then you can always say, okay, well, I need to be at the point x is 1 and y is 3. So I could just put in 1 and 3 and solve for my t value. Because I can see that when t is equal to 0, I'm at the point 2,5. So I just have to figure out the t value to get me to the point -1, 3. And then solving, you should get a -2 for t on both sides. Okay, so I've already done 3 different parametric representations for that one line segment. Again, I can do this infinitely. You or my lab will usually go for the first most intuitive solution, but you never know, sometimes not. Example 6, we want to find a set of parametric equations that represent the path from 1, 3 to -5, 4 to 0, 7. So you got to be careful here. This is a path, and it says from one point to another, so we have a direction. We're going from 1, 3 to -5, 4, but then we're also going from -5, 4 to 0, 7. So I have direction. I have to take that into consideration when I make my parametric equations. And I actually have 2 line segments, so I'm going to have 2 sets of parametric equations. Well, let me do a quick sketch of the graph, and this is not going to be to scale. Let's say I have 1, 3, and then I'm going to -5, 4, and then I'm going to 0, 7. So I'm going to have something like this. Again, definitely not to scale. I just want to get a picture in my head of what's going on here. So if I start at 1, 3, and then I go to -5, 4, and then 0, 7, that means I'm going to have to describe this first piece with one set of parametric equations, and then we'll consider the other piece in just a bit. Okay, So if I go from 1, 3, 2, negative 5, 4, since I'm starting at 1, 3, that's going to be my starting x sub 0, y sub 0. I need my b over a, so I need to find my slope. It's always ending minus starting, so it's going to be 4 minus 3 over negative 5 minus 1, which would give me a 1 over a negative 6. I'm going to leave that negative in the bottom. I could put it in the top and have negative 1 over positive 6. It's still the same number, but I want to leave it exactly as it is so that I have the correct b over a, and that's going to make a difference with direction. Okay, if you did sort of move things around a bit and it wasn't going in the correct direction, that just means change your negative. My x value is going to be 1 minus 6t. My y value is going to be 3 plus 1t, or t. So my t values, when t is equal to 0, I'm at my starting point 1, 3. When t is equal to 1, I'm at the point negative 5, 4. Okay? And if you didn't see that it was 1, what you would do is put in an x value of negative 5 and a y value of 4 and solve for t. This is just one piece of the path. However, you have to be careful because this is t equal to 0, t equal to 1. We're supposed to be continuing on with our path, which means that I have to continue on with t is equal to 1. So let's think about this. I'm going from negative 5, 4 to the point 0, 7. And my t value is 1 because I'm continuing on with my t values. I can figure out my slope. My slope is going to be the ending point 0, 7 minus the starting point negative 5, 4. So that's going to be 7 minus 4 over 4 plus 5. 4, why did I put 4? 0 plus 5. Sorry. So that's going to be 3 over 5, which would give me my b over a. This is what I have so far. I have my x value for this second line segment as being an x sub 0 that I don't know yet, plus my a is 5, so plus 5t. And my y equal to this y sub 0 that I have to figure out, plus 3t. However, I know my starting value at the point negative 5, 4 is t equal to 1. And in fact, I know my x value is negative 5, so I can write this as negative 5 equal to x sub 0 plus the 5 times the t value of 1. So when t is equal to 1, I'm at the point negative 5, 4. If I solve for x sub 0, I get negative 10. And I'll do the same for my y equation. I know that my y value is 4 plus 3 times my t value is 1, which gives me a y sub 0 of 1. All right. So I have x is equal to negative 10 plus 5t. Y is equal to 1 plus 3t. My t values start at 1, and they should go to 2. Notice if I put in 2 for t, I have an x value of 0 and a y value of 7, which is what I need. If you don't see that, then you can algebraically solve for your t value by putting in the ending x value of 0 and solving for t. And then when you solve for that, you should get that it's 2. And then we'll double check by putting our ending y value of 7. And then solving, if we minus 1, it's 6, divided by 3, it's 2. So again, you should get the same t value. If you get different t values for your x and your y as you're going through the algebra, that means something got messed up along the way. We looked at circles, we looked at lines, but there's other curves as well. Now, when you're dealing with other curves and you have to find a parametric representation, it just depends on the type of curve. What you're going to look at is you're going to look at, remember, you have to split up an equation that just has x and y and figure out how you can get a t in there. In example 7, it says find a parametric representation of this parabola, and we have x values from 0 to 2. So remember, when we set our parametric equation, remember we are going to set our t values. So it seems reasonable to me, looking at this problem, that if my x values are going from 0 to 2, perhaps I can just, let my x value be my t value. Again, this is not unique. So if I let x equal t, then that means my t values are going to go from 0 to 2. And then all I have to do in the y portion is substitute in t for x. And I'm actually done with this. Now I can double check. I can go ahead and graph my original parabola that I was given. Okay, so it's a parabola, it's opening down. I can see that it's going to pass through 0, 4 and 2, 0. So this is not the parametric representation that I came up with. This is just the parabola that I was given with only x values from 0 to 2. So when x is 0, I'm at y value of 4. When x is 2, I'm at a y value of 0. Notice that this doesn't say anything about the way the curve is generated. If that information was there, then I'd have to adjust a little bit. Maybe, who knows, might not. Okay, so now let's look at the parametric representation. X is t, y is 4 minus t squared, where t values are going from 0 to 2. So when t is equal to 0, that means I'm at the point x is 0, y is 4. When t is 2, I'm at the point 2, 0. So this particular representation does give me the same curve, and it gives it to me generated downward. So let me just change this a little bit. What if we had to have a positive orientation upward? Orientation, that's why I use generated. Well, the parametric representation that I gave showed that it's generated downward. So remember to change the direction. If it's positive, go negative. If it's negative, go positive. So let me change this to x is equal to a negative t. Well, that would also mean that in my inequality, I would replace the t with a negative t as well. So I'd have 0 less than or equal to negative t less than or equal to 2. But if x is equal to negative t, then y is equal to 4 minus negative t squared is still going to be t squared. So it's going to look like this, negative t squared. So y is equal to 4 minus t squared. That hasn't changed. So I got my x, I got my y. Usually we don't want to have the negative on the variable, so I'm going to have to multiply this inequality through by a negative. So it's going to be 0 multiplying by a negative, means I'm going to flip the sign. In other words, my t values are going to go from negative 2 to 0. Did that give me the upward orientation that I need? Okay. So we're starting with the smallest t value of negative 2. When t is equal to negative 2, with this particular parametric representation, my x is positive 2 and my y is 0. So I'm starting here at 2, 0. And then my t's get larger when t is 0, I'm at the point 0, 4. So yes, it did change the orientation. So again, the more conditions you're given, the more you have to take that into consideration when you come up with your parametric equations. So what we've done is we've reviewed parametric equations, different types, and so on. But now we're going to look at applying our calculus techniques to these parametric equations. One thing we always do in calculus is we find derivatives. So how do you find a derivative for a parametric equation where your x value is written in terms of t and your y value is written in terms of t, or rather they're functions of t? Well, when you find your derivative, you can simply take the derivative dy over dx, our normal derivative. Algebraically, if I divide the top and the bottom by dt, then I get dy over dt, dx over dt. In other words, this is the derivative of y with respect to t over the derivative of x with respect to t, which is super easy. So to find the derivative of a parametric equation, you just take the derivative of the y function over the derivative of the x function with respect to t. In example A, we want to determine if there are any points where this curve has a horizontal or vertical tangent line. So remember, when we say that the tangent line is horizontal, that means its derivative, and I'll do dy dx, is equal to 0. If we have a vertical tangent line, that means our derivative, which is simply the slope of the tangent line, is undefined. So the first thing I need to do is figure out what the derivative is, set it equal to 0 to figure out where we have a horizontal tangent line, and look at where it's undefined to see if there's a vertical tangent line. If any, there may not be any points, but these are points. Remember, the points on the curve are not the t values, they're the x and the y values. Those are our points. So since we only need to find the x and y, one strategy I could use, which is I think what my lab does most of the time, is simply get rid of the parameter t and only work with in terms of x and y. However, we could also keep it the way it is, use this derivative formula to figure out the derivative, and then look at where we would have horizontal or vertical tangent lines. So I'm going to do it both ways. And the way you choose to do it kind of depends on the parametric equation that you're given. One way may be shorter than the other way. So let's look at just computing the derivative here. The derivative is going to be the derivative with respect to y is going to be cosine of t. The derivative with respect to x is going to be negative sine of t. So I have my derivative. If the tangent line is horizontal, that means that this derivative is going to be equal to 0. It's a fraction. The only time a fraction is equal to 0 is when the numerator is 0, but the denominator is not 0. So really we're looking at, where cosine is equal to 0. And cosine is equal to 0 at t equal to pi over 2 and 3 pi over 2. Okay, I don't know if you recognize this, but if x is cosine, y is sine. This is actually just the unit circle. Okay? Center at 0. So I'm just going to go ahead and sketch this parametric equation. And I'm going to do one cycle around. Well, it's clear to see that we have horizontal tangent lines in two places. Here it would be an x value of 0 and a y value of 1 at the top. Bottom would be 0, negative 1. Well, let's look at where cosine is equal to 0. Cosine is equal to 0 when t is equal to pi over 2. Well, if t is pi over 2, my x value is 0 and my y value is 1. So that would be at the point 0, 1, which is exactly what I expected from the graph. And then when t is equal to 3 pi over 2, we get the point 0, negative 1. All right, so what about vertical tangent lines? Well, vertical tangent lines means that the slope is undefined, or the derivative is undefined. On my graph, I can see that I have two vertical tangent lines, and I know what these points are. This would be the point 1, 0 and negative 1, 0. Well, is that what I get when I algebraically figure out where this derivative is undefined? So the derivative is going to be undefined when the denominator is equal to 0. So that would be where negative sine is equal to 0. And I don't care about the negative, multiply that through, I get sine is equal to 0. So sine is equal to 0 at t is equal to 0 and t is equal to pi. Well, when I put in 0 for t in my parametric equation, I get the point 1, 0. And then when I put in pi, I get the point negative 1, 0, which is exactly what I expected to find when I looked at that graph. So this is a strategy of keeping everything in parametric form and then finding the x and the y values, given the t values that you solved for. However, you can always just switch to x and y and then stay in x and y. This is the unit circle. This is x squared plus y squared is equal to 1. So I got rid of the parameter t, and I have the equation only in x and y. So now what I would do what I'd normally do from Calc 1 is I would go ahead and solve for the y, and I would get plus or minus the square root of 1 minus x squared. Unfortunately, I have two functions that I have to find the derivative of. Remember, the goal here is to compute the derivative, see where the derivative is 0 and where it's undefined. So if I look at y equal to the positive square root of 1 minus x squared, and I compute the derivative, and I'm not going to go through all the steps, it'll turn out to be negative x over the square root of 1 minus x squared, so you can just verify that. But remember, I also have y equal to negative square root of 1 minus x squared. the derivative here would be positive x over the square root of 1 minus x squared. So I have these two derivatives I have to figure out for horizontal where they're equal to 0. So horizontal means that the derivatives are 0, and they're only going to be 0 if their numerators are 0. So that would be when x is equal to 0. And if x is equal to 0, then the y value, plugging it in, is going to be plus or minus 1. So that gives us the point 0, 1 and 0, negative 1, which is exactly what we expected to find. Now, if we're looking at vertical tangent lines, that means the derivative is undefined. So that means 1 minus x squared has to be equal to 0, which means that x has to be plus or minus 1. If x is equal to plus or minus 1, then the y value is 0, right? I'm putting it back into the equation to find the corresponding x or y value. And that gives me 1, 0 and negative 1, 0, which is exactly what I expected to find. So again, you can keep the t, take the derivative, go from there. If it turns out that that's a little bit difficult, then get rid of the parameter t, take the derivative as you normally would from single variable calculus, and then work from that. Let's change this up a bit. In example 9, let's find an equation of a tangent line. We're given a curve, and we're given a t value in which to find the equation of the tangent line. All right, so since we're trying to find the equation of a tangent line, we're going to, again, it's not going to be in parametric form. When you work here with these derivatives, the goal is to get points in x, y, and if you're trying to find a tangent line, the tangent line with just x and y is sufficient. You don't need to know which direction the tangent line is generated in. So since we're finding the equation of a tangent line, we're just going to use our normal algebra formula. Y minus y sub 1 is equal to m x minus x sub 1. So I need a point and I need a slope. The slope is the derivative. I know everybody knows this, but sometimes people forget. So how do I get the point? Well, I have a t value. All I have to do is put in 3 for t, and I have an x value of 5. So the point that I'm going to be using my x sub 1, y sub 1 is 5, comma, put in 3 for t, and the y value is going to be 27 minus 3, or 24. So this would be my x sub 1, y sub 1. I just need my slope. So my dy dx is going to be the derivative with respect to t for our y equation is 3t squared minus 1. The derivative with respect to t in my x equation is 2t. And I'm supposed to evaluate the derivative when t is equal to 3. Okay, so when t is equal to 3, this should be 26 over 6. And that reduces to 13 over 3. And here it is appropriate for us to reduce because our equation does not have the parameter t in it. This would be y minus 24 is equal to 13 over 3 x minus 5. And in my opinion, that is fine. However, oftentimes on my lab, if you get a question like this, they'll want you to write the equation of the tangent line in slope-intercept form, so solving for y. To get 13 over 3x, let's see, minus 60 minus 72, minus 7 over 3. Double check me on that, you guys. So we looked at applying derivatives to our parametric equations. The last thing we're going to do is look at integration with our parametric equation. And one thing we could do is we can find the length of our curve. We call that arc length if it's given in parametric form. So let's look at our x value. Remember that was a function of t in parametric form, and our y value was a function of g. So let's just suppose that the derivatives of x and y are continuous. And let's say the curve is traversed only once, which means it doesn't double up on itself and keep going over and over the same curve. We're just going to go once. From some point A to B for our t values. Then our arc length is between the 2 points. Remember, these are y values. So this is our starting and our ending point. So the arc length, or the length of that curve between these 2 points, is given by this integral formula. That square root there is going to give us problems. Oftentimes when you integrate and you have square roots, you have to either do like a substitution, or you have to try to get something like a perfect square underneath the square root so the square and the square roots cancel. They're difficult to work with. So in this case, if you can't find a strategy that gives you something nice, that gets rid of that square root, then you're kind of stuck with using a calculator, which is often the case in these examples. Well, what I wanted to do is just look at where this formula comes from. Now, this is just a sketch of an idea. I'm going to look at a curve. I'm going to keep this in black. Just some random curve. So let's say I wanted to figure out the length of this curve from some A value to some B value. Okay, so let's look here. Well, usually with integrals, what we do is we start out doing some partitions, right? And then we make those partitions really, really, really small. We take the limit. So go back to your Riemann sums. Now, what I'm doing is I'm connecting line segments on these intervals. And these line segments, I can compute the length for each one of those. So when I add up all those lengths, that would be an approximation of the length of this curve, or its arc length from A to B. To find the actual length, I would have to make these really tiny, tiny partitions, make them really small, take the limit. Oops, and this first one shouldn't be here because that's before A. Bye-bye. Okay. So let's go ahead and look at how we compute this length. Remember what we're doing here, maybe I'll zoom this in, is we're going to be dropping a right triangle where the length of the x would be a delta x, that's the distance of the x values, and the distance on the y would be a delta y. So this length here is going to be the hypotenuse, and I'll call it L. By the Pythagorean theorem, all we're doing here is we're using that if you square one side and add it to the square of the other side, it's going to be the square of the hypotenuse. But we don't want the square of the hypotenuse, we just want the hypotenuse. So if we square root both sides, we get that the length is going to be the square root of this delta x squared plus delta y squared, the distance of the x, the distance of the y. Now remember, this is an integral. The strategy here is to take our limits and start partitioning these into smaller and smaller and smaller and smaller pieces. So what happens there is then this becomes a more accurate estimation of the length, and as those partitions get tinier and tinier and tinier, we actually do get the length. But what happens is, remember the difference between a delta x and a dx, the differential dx. is the dx is what happens when that delta x, when its limit goes to 0. So really this delta x is going to turn into that differential dx, or the derivative of x. And we're squaring that, plus the derivative of y squared. This is just a rough sketch, a rough idea. If you want a more formal proof of this arc length formula, there's a really nice one in your textbook. But then the derivative of x, remember x is just a function of t, that would be f of t squared plus y is a function of t as well, but it's prime because we took the derivative, sorry. So then it's g prime of t squared. And that's where this formula came from. So sometimes it's nice just to discuss where those formulas come from. We'll see this again too in Calc 4. Example 10, we want to find the arc length of this curve for the given interval. So since we're given an interval, 0 would be our a, pi would be the b. And those would be our limits of integration. X is e to the t times sine t. That's going to be our function f with respect to t. Y e to the t times cosine of t, that's going to be our function g of t. So all we have to do to figure out the arc length from 0 to pi is first figure out the derivative of f and the derivative of g, and then square them. So f prime of t, we have to use the product rule here because it's e to the t times sine t. So I'm going to take the derivative of e to the t, which is e to the t. I'm going to keep the sine t, plus keep e to the t derivative of sine is cosine. But I don't just need f prime of t in the formula. I need f prime of t squared. So it may be easier to, instead of squaring that whole thing and foiling stuff out, maybe factor out the common e to the t. So I have sine of t plus cosine of t. Don't have to, but I kind of see it that way. So when I take the derivative of f and I square it, it's just simply e to the t squared. And then when I square sine t plus cosine t, it's going to be sine squared t plus cosine squared t plus 2 sine cosine. Okay, again, that's just how I see it. You could have left it the way it was. Now, g prime of t, it's going to be similar. So product rule, I'm going to take derivative of e to the t, keep cosine t, plus keep derivative is negative sine. And then when I take g prime of t and I square it, again, I'm going to look at factoring out e to the t. This becomes cosine of t minus sine t. So squaring the e to the t, and then the square in the parentheses would be cosine squared plus sine squared. Minus 2 sine cosine. All right, so I'm going to pause for just a second. Notice that in f prime of t squared, the sine squared cosine squared is 1. And g prime of t squared, cosine squared plus sine squared is 1. So that simplifies those even further. And if you can see by adding the f prime of t squared and the g prime of t squared, if you can see that if you add them, that the 2 sine cosine minus 2 sine cosine will cancel, you could do it now. So let me show you what I mean. I'll write it all out. So the length is going to be the integral from 0 to pi in this case. Is that what our t values were? Yes. Square root, oh, it's going to be a long one, of e to the t squared. And the only reason why I left it as e to the t squared instead of e to the 2t is because I know that the square root and the square will cancel each other out. So for me, it's easier to see that way. In parentheses, 1 plus 2 sine cosine plus g prime squared is going to be e to the t squared 1 minus 2 sine cosine. I never make my bar long enough. dt. So you see in each one of those terms I could factor out the e to the t squared, and then the e to the t squared and the square root would cancel. This becomes the integral of e to the t. What's left after I take that e to the t squared out from underneath the square root is going to be 1 plus 2 sine cosine plus 1 minus 2 sine cosine, which leaves me with the square root of 1 plus 1, or 2. All right, so that constant square root of 2 stays. The integral of e to the t is e to the t, so this is square root of 2 e to the t. Evaluate it from 0 to pi, which is simply square root of 2 times e to the pi minus the square root of 2. And that's where I would stop. Oftentimes your MyLab will have you factor out the common square root of 2 and in parentheses put e to the pi minus 1, but that doesn't matter to me. This is kind of a long section. We've gone through a lot of topics, but that's it for 12.1.